Welcome to the CompTIA A+ 220 1101 Core 1 exam, Objective 2.5, DNS Configuration. DNS is the domain name system, and we often refer to this as the service that converts the fully qualified domain names that we might type into our browser to something our networks might use, like an IP address. But what you may not realize about DNS is that it is not simply a standalone server that provides this resource. There are multiple servers across the internet that provide these translations and how they work on a hierarchy across the different fully qualified domain names. This is also a very distributed database because we may have different DNS servers on the internet. There are 13 root server clusters. In actuality, this consists of over 1,000 different servers. There are hundreds of generic top-level domains. These are the .coms or .orgs or .nets, and then there are country-level, top-level domains for US, USA, UK, or United Kingdom. Here's a very simple visual representation of this hierarchy from the perspective of the root. We'll start at the top with a period. This designates the end of the fully qualified domain name. And working backwards, we would have a .com, a .net, a .edu, and others. In very large organization networks, you might have domain names, for example, Berkeley, and subdomains like CS. Having this hierarchy allows us to configure very specific structure, and this works across every fully qualified domain name on the internet. If you'd like to see visually how this translation operates and your system supports the dig command, you can run at the command line dig. The result of this command shows a summary of what we requested, so I did a dig command for google.com. It shows us the information we sent specifically for google.com. And this is a generic dig. We didn't specify anything. There's no commands or arguments. Okay, in the answer section, we can see that it replies with an IP address. If you're not on a system that supports dig, then you can use NSLOOKUP and get similar results. Behind the scenes, the DNS server has a large database that contains fully qualified domain names, IP addresses, and other details that can help your systems perform this translation between fully qualified domain names and IP addresses. We refer to these as resource records, and in this video we'll look at a number of different types of resource records and how they're used on a DNS server. There are over 30 different record types. We won't go through all 30 in the video, but we'll go through some of the most common ones. As you can imagine, a DNS server is a critical resource. If a DNS server isn't available to make a request, behind the scenes there's translation between domain name and IP address. This is why we tell people you're making a change to DNS, you have to have good backups and know previous configurations of what you're changing in your server. You might also find that DNS service that you're using can provide you with a web-based front end, so the configuration that you need can be done from a browser. You don't have to have all these complex tools and understand different records. You just need to know the configuration file and to be able to add a record from the web-based version. The first record we'll look at, and perhaps one of the most common records you see in a DNS server, is an address record. We often refer to this as an A record or a quad record. The A records are address records for IPv4. So this is a record that will have a fully qualified domain name that's associated with an IPv4 address. The Quad A records are for IPv6 address. The same thing applies. We'd have a fully qualified domain name that matches an IPv6 address. If the front end of your DNS server is the web-based configuration, it's the same information, but we separate out the A record, the host name, the IP address, and the time till live for this IP address. The time to live in a DNS server is specifying how long an end station will remember this match between fully qualified domain name and IP address. This 15-minute time to live means that a device will make the request to a DNS server and store or cache that information for 15 minutes. After 15 minutes, that information is removed from the cache, and the device needs to communicate back to the server. It will need to make a request again. It's quite easy to edit a DNS record from the web version. You can just edit a record and look at different configurations. You can see the host name, you can see the address, and you can see the TTL. Another important record in a DNS is where all of your emails should be delivered. This is a mail exchanger record or an MX record. To make this work, you would need two separate records inside your DNS server. The first would be an MX record. You can see the mail exchange record points from Gmail to several SMT sites. DNS servers have many different functions they can provide. One of those is stored text that can be used for other purposes. We would store text information in a text record or TXT record. This is usually public information. Since people are able to query these text records on your server, these text records were originally designed for very informal purposes. But today we have very specific uses for a text record in our DNS server. For example, we might need to use this for verification purposes. We might be making a configuration change to our domain, and the domain change requires you to add something very specific to a text record in your DNS server. We also use this text record extensively for our email security, and you'll see in a moment how we're able to add information to a text record that can be very helpful to verify the origin of a particular email. You could use an NS lookup and have it match the type of record to a text record and verify its domain name. For example, I have google.com. You can see that when you perform a google.com lookup, that Google has a number of text records on their device, which include things like Facebook domain verification, a Google site verification, a DocuSign text record. So you can get a lot of information from looking at these records. A common text record that you might find is an SPF record, or a sender policy framework. This is a list of all of the email servers that you are authorized to send messages using your fully qualified domain name. This was created to help prevent others from spoofing your fully qualified domain name and sending email as if you would send it from yourself. A mail server receiving an email that says it was from a particular website will query this DNS server and retrieve that SPF record in the DNS server. And it can determine if it's authorized to send it to this host or not. We can even take this email security one step further and provide digital signatures that we can associate with outgoing mail. We do this through the use of DKIM text record, or domain keys identified mail. This is going to be validated by the mail servers as that message is traversing through the network, and the public key associated with this digital signature is added to a text record in the DNS server. You might create a DMARC record on your DNS server that says if a message is not validated, Simply accept it, or maybe send it to a spam folder, or simply reject the email entirely. The mail servers behind the scenes keep track of how many mail messages have been validated and how many have failed the validation. And then you can receive a report that shows exactly how many messages were able to get through based on the SPF or DKIM configuration. Here's an example of adding one of those demarked text records to your DNS. You can see that content specifies what to do with the email message and where to send the report. Okay, we're at the end of Objective 2.5. Here's a pop quiz. What command line tool does Linux use to look up domain names? A. Traceroute, B. Ping, C. NSLOOKUP, or D. Dig? And the answer is Dig. Most Linux systems use Dig to find domain name system information. Thanks for watching.